I'm going to. Whoa, that's the wrong one. Okay, I'm gonna just go over this because some people may not have used zip files before. I know most of you probably have, but I'm gonna walk through that part once, and I'm recording it, so if you need to go back and watch it later, you can. So I'm gonna go all the way through getting the data, unzipping it, and using it. So we're here on week 2. Okay, and go to activities. And then under lab 2, you'll see the zip file. And it'll just download. If you click on it, it just downloads it for me. Depending on what browser you're using, like I know IE is installed on some of these. Okay. Anyway, that's like the third time I downloaded it. Oops. Lab 2 update, right there. So I downloaded it. You might press refresh or clear cache or something if it downloaded a previous version. All right, so I'm just gonna right click on it and say open. Okay. Now once you do this, you'll notice that this lab2 update.zip, it's an archived file. In other words, it's a zipped up version. It's a bunch of files that are inside of another file. You have to take them out in order to work with them in ArcGIS or anywhere else. So I put them all in one folder called Lab 2. So what you can do is right-click on that Lab 2 folder and copy it and save it somewhere where you can use it. That's what I'm going to do. I'm going to right-click on Lab 2. I'm going to copy this, and I'm going to find a place to save it. Maybe I'll make a new directory in the C drive called GIS, and I'll paste it into there. So now I have GIS Lab 2. Maybe on your computers it won't let you save right into the C drive. Anybody having trouble doing that? Or does it work? Has anybody done anything like I just did? You just put it on the C drive and it worked? Okay. All right, working? Okay. All right. So now I have it under C, GIS, Lab 2. And if you go into the Lab 2 folder, you can see that I have a Word document file, a Word doc, and I have another folder that's just called Coordinates Projections. The earlier version of this file, of this one, this was all empty. It was blank. There wasn't anything in here. Okay? But this one has stuff in it. So a few things I want to point out really quickly is that notice that these files all have the same name except for they have a different extension. And maybe you can't see the extensions in on your computers. I'm not sure, but that doesn't really matter a whole lot. Okay? What I want to point out is that this is one GIS data layer, or one layer that we're going to bring into ArcGIS. And it actually contains multiple files. Even though we commonly refer to this group of files as a shapefile, one shapefile. We usually use the singular term. We say that's a shapefile, this is a shapefile, that is a shapefile. A shapefile is a file format that's used for storing vector GIS data. So, although it is multiple files, it's storing one vector GIS data layer. Okay? And you'll see that it's only one layer when we bring this up in ArcGIS here in a second. All right, so the first thing I'm going to do is open up the lab. This is Lab 2. And this time I did add this line here. It's due 2 weeks after assigned, which is today. It's due 2 weeks from today. All right? I think this one actually is, there's no big writing assignment. I shouldn't say big. There's no writing assignment. There is a couple questions to answer, but there's no page to write up today. All right, so what we're going to do is add our own data to to the data view. We're going to modify the projections of some data, and we're going to be setting the scale, and we're going to be introduced to the measure tool. It's going to help us to measure distances in our GIS. I already walked you through this part, so now you'll see that we have 3 different layers to work with. Okay? So let's go start following through this. I'm not going to go all the way through it. I'll just start going through it. I'm going to talk about a few other things that I think are important, and then I'll turn it over, and GHY and I can help you if you have any additional questions as you're working through it. All right, so the first thing I'm going to do is open up ArcGIS, which I've already opened. You might have to find that ArcMap. Sometimes I like to just press the Windows key and type in ArcMap, and then press Enter. But you have to open it up like this. Your computers, it probably looks a whole lot better. This Dell laptop is really lame how it makes everything small. Let's see how it looks. Yeah, it looks normal on your computers. But I've got, like, it's cut off here. I want to write a nasty letter to Dell and say, what's going on? It's probably operator error, which means it's probably my fault, but I don't know how to fix it. So I have this little teeny weeny button right here. If I hover over it, it says add data. I don't know how to make it bigger, but it's got a plus sign, and then it's got a yellow triangle underneath. I'm sorry? Oh, okay. Close this out. This is ArcGIS Pro. Probably use that sometime later in the semester. But right now we're going to use ArcGIS with that. We're going to use ArcMap. Yeah, ArcGIS has released, last year they released another piece of software called ArcGIS Pro, and it allows us, it's probably eventually going to replace ArcMap, but right now they're kind of like simultaneous products. But it does 2D and 3D at the same time, so that's kind of cool. But it doesn't have all the tools. We're not, I'm sorry, I'm explaining what ArcGIS Pro is. We're using ArcMap. ArcGIS Pro is kind of a new version of the software, and I'll try to make some of the labs use that software, but we're not doing that yet. So we're using ArcGIS. So it's a little add data button. If there's anybody that can't find this button, just raise your hand, and GHY will help you locate it. Okay? Yep. Add data button.
Okay.
Yeah, or Corey. Hey Corey, you need to leave at 4, right? Or 3:30?
Yeah.
Okay.
Yeah, I'll probably leave a little before 4.
Okay. So I won't talk for much longer, but all right. So so now we have to navigate to the location where you unzipped that data or took that data out of the zip file. All right. So I hit the add data button, and I'm going to find that data on disk. So I put it in C, GIS, Lab 2, coordinate projections. Now you can see these 3 layers there. You might have put it somewhere else. Okay. I'm going to add all 3 of them into the map. Because that's what it says to do, I'm pretty sure. Okay, yep. So I'm going to go there and add all 3 of them. So it should look like that when you add them all to the map. And I can help people out. Anybody else need help getting it? Okay, so the question is, why are mine different colors? Mine are purple too, but your country, sorry, my lines are purple and yours are red. So ArcGIS assigns its own, whatever colors it decides. So yours are blue, yours are purple, mine are green. I don't know what random color quicker it does. But, we will learn a little bit about changing the colors. This class is a little more about analyzing the data. But let's say you wanted them to be green instead of purple. You could double click on the word, this one, in this case, it's USA 04. And you go to symbology, symbology. And you could change the color to any color you want. I'm going to change it to blue. I just made mine blue. All right, what do you think that the purple on my screen, what do you think those lines represent? Yeah, they do, exactly. They represent latitude and longitude. Sometimes, we often refer to that as a graticule. Those latitude and longitude lines are the graticule. And we can see, I think we did talk about this a little bit last week. If we click the little information button, if we click on one of these, it'll pull up the attribute value for that line segment. So it actually pulls up and says that this is 120 degrees west that I just clicked on. And this one right here is 15 degrees east that I just clicked on. So it looks like they're increments of 5 degrees. So this is a 5-degree increment graticule. Every 5 degrees this way, every 5 degrees this way. If I want to, I can right-click and open the attribute table, and now I can see. Oh, that's for USA. Well, that's fine. This is the attributes for for USA. So if I highlight on one of these, there's Washington. So these are the attributes for Washington. All right. One of the things that's kind of interesting is, remember I told you that all this data was in latitude and longitude. So this area here for Washington, what units is that area in? Washington, 20.75 meters. Meters isn't even really a area measurement, right? It's a linear measurement. So that was a good guess, but these numbers aren't really valid because they're what happened is we took Cartesian coordinates and we tried to measure the area. So that number 20.75 is in weird, not real coordinates. It's the latitude and longitude in degrees, pretending that they're Cartesian coordinates and calculating the area. 20.75 square degrees. It doesn't really exist. There's no such thing as square degree. So these numbers are right. Okay? But interestingly, like I said, and this isn't in the lab, but I'm gonna do it anyway. You don't have to follow along with me if you don't want to, but I'm going to first of all clear this selection, and then I'm going to do something that we'll do next week. I'm going to add a new field, and I'm going to call my new field A area. In my mind, that's standing for actual area, although that might not be a good thing to call it. I'm going to make this new field. I'm going to make it a double. In other words, I'm going to make it a really precise number that has lots of decimal places. That's what a double is. A float has a few decimal places, but not that many. Double has a lot. All right? This isn't in the lab. This is something that I'm doing to actually calculate area here real quick. My mouse is gone. There it is. Okay. So one thing a GIS system will allow me to do is right-click on this and say calculate geometry. And I can calculate a few different properties. The property I want to calculate is the area, so I'll come down and do area. And okay, this is what happens when you get off track. what I have to do before I do that is it's not allowing me to calculate the area because it knows that I can't calculate the area based on decimal degrees. So I first need to change the projection of the data frame so that it has a projected coordinate system to calculate the area using. Okay, so see, when I said calculate geometry, I get an error. It's not working. I thought that it was going to let me like choose a map projection. So what I'll do is this is in the lab. Let's see where it is in the lab. Oops, that's last week's lab. Okay, so this is right in the first part of the lab here. That's fine. So from data frame properties dialog, choose coordinate system. Then we're going to choose a predefined folder. We're going to choose projected coordinate system, continental, North America. Then select North America, Lambert conformal conic. Okay, sounds like a lot, but that's pretty quick. Watch, I'll do it. So we're going to right click on layers and say properties. And then go to coordinate system. It's one of the tabs. Coordinate system. And then we're going to choose projected coordinate systems. And North America, or continental, then North America, and then, what did it say, Lambert conformal conic? North America, Lambert conformal conic. North America, Lambert conformal conic, right there. Okay. So before I hit OK, here's all the projection parameters for that. So there's really no false easting or false northing. This is a continental wide projection. It's not really meant for taking precise measurements off of. So there's really no reason to have a false easting or false northing. But there is a central meridian and a couple standard parallels. Now we know what those are. Those are the areas where the map projection is the most accurate. If we go down here, we can see the datum that was used. In this case, this datum, see how it's indented here? This datum was based off of this spheroid. Okay, and it's labeled spheroid in here, but technically we know that this is actually an ellipsoid. Why do we know that it's an ellipsoid? Because the semi-major and semi-minor axes are different. Okay? If they were the same, it would be a spheroid, a true spheroid, a sphere. But this always says spheroid, that's just the software. Okay? So this datum has this spheroid associated with it, and it has this semi-major, semi-minor axes. This is basically the ratio of these two numbers. Okay, this inverse flattening. Okay? They don't specify where the tie point is, but it's tied into this datum as well. So notice that we didn't have to specify any of that. It's just part of that standard projection. And as soon as I say OK here, it's going to transform that view from, I'm going to go ahead and close this, or yeah, I'll close it. I'm going to go ahead and close this for a second. It's transforming that view from using latitude and longitude as a Cartesian coordinate system. It transferred it to a Lambert conformal conic projection. So if we zoom in here, it looks right. Now imagine if we had the whole Earth, which we don't have, if we had all of the countries here. Imagine if we had South America down here. It would start to look really big and weird, right? Well, this coordinate system wasn't created for looking at South America, so it doesn't really matter. If we had Russia and the rest of Asia, it would be like all arced up there and looking funny as well. In fact, the middle of the ocean would be split apart at this point over here. But if we zoom into just this part of the world, it looks good. In fact, if we zoom into just the lower 48, well, that looks like a map that you might find in a textbook. It's a very good coordinate system All right. Now, getting back to my tangent that I was about to go on, is that you don't usually go back to a tangent. Only I do that, I guess. This is not in the lab. If I right-click on this guy and calculate the geometry and go, I'm doing this a little fast. So now I'm using the coordinate system of the data frame. I can't use the coordinate system of the data source because the data source is still in latitude and longitude. So that's an important thing to think about, is that we're storing our coordinates in one coordinate system, and we have the option in most modern GIS software packages to view them in a different coordinate system. So when we chose the Lambert conformal conic coordinate system, when we chose that, and you saw the view shift, it actually did not change all of these little coordinates that are defining the states of the United States. It didn't change any coordinates. It just moved them and recalculated on the fly. In fact, what we call it is projection on the fly. So on the fly, it's doing all the math to convert between latitude and longitude and that projection, because it's all math. All that projection and coordinate systems is math. And so it's converting from latitude and longitude to Lambert conformal conic really quickly and showing you where it would be if it was in in Lambert conformal conic in that projection. Okay? So that's why there's this distinction. Use the coordinate system of the data source, or use the coordinate system of the data frame. And I forgot who it was. Somebody asked a question, and then I responded and said, well, modern GIS systems are kind of capable of doing this on the fly. So we can calculate this area and then create another column and calculate the area and create another column and calculate the area and see how the areas changed in different projections. So what I'm going to do here is I'm going to choose square miles because that's not really a scientific thing to do, but miles are a bigger unit of measure, and these are going to be big because they're state areas. So I'm going to change this to square miles and say OK. So now I can see that, I'm pretty sure this is still Washington. I can see that Washington is 60,125 square miles in terms of its area, and so on. These measurements are still based on this map projection, and we get different values if we change the map projection. Okay? So if we chose a map projection that was just for Washington, we could get a more precise measurement for just Washington. And then we chose a map projection for just Oregon and so on. We could get these numbers down so that they were more accurate. I should say accurate, not precise, because the precision is actually pretty high, although the accuracy is questionable because we're using the whole United States. All right. So that's my little tangent showing those coordinate systems. So what you're going to do is, instead of I kind of walked you through how we could calculate area in different map projections, right? So what we're actually going to do in this lab, the rest of this lab is going to walk you through. It's going to walk you through measuring distances and locations in different projections. So what you're going to do is follow the lab through and then find the latitude and longitude for these places and find the XY location of those places, and then find the distance in miles between Columbia and these places. So all these cities are marked. If you don't know which one's which, I'll give you. So we're doing everything from Columbia. Should probably change this so that it's doing everything from Hattiesburg or from Gulf Long Beach. But this is Columbia, South Carolina, and that's Florida. That's Miami. That's Key West. This is Nashville. That's Memphis, and so on. Los Angeles is over here. You could open up the attribute table if you're having trouble finding out, like if you're not familiar with the United States and you don't know that this is Jefferson City, or is it Columbia? It's Columbia. If you don't know that's Columbia, Missouri, then you could open up the attribute table and you could find the city you're looking for in there. Like, let's say you're looking for Denver. Don't know where Denver is. Oh, there it is. Okay, Denver's that city. All right, and then the other thing that you're going to use is, to do this, you're going to use the measure tool. The measure tool is right here. So you can click on, you can hover over a point and it'll snap to that point, and then you can click over to another point. There's the next point. And so that's the distance there that it's reporting. Anybody have any questions? So you basically just calculate those distances in two different coordinate systems, and then you answer some questions, but the questions aren't like, they're just little, 3 or 4 sentence type answers. Yeah.
I have a serious question. The first one is when you go to measure. So right here, I click from there to there, and now I want to stop measuring.
Okay, double click when you want to finish.
Okay, and that just leaves.
Yeah, but you probably want to double click on the second one.
Okay.
There you go.
Also, how do I convert this from meters to miles?
So hit this guy. No. Or hit this guy. Distance. Miles. Okay, so that's a good question, so I'll go ahead and demonstrate that for everybody. Okay, so I'm going to get, instead of getting meters, because I want you to report it in miles, I double click. Okay, that gives me, so you double click to finish, and then it's the second little drop down. You choose distance, miles, and it'll switch it to miles for you. All right, any other questions? And then one other thing that, well, I'll